from Jiangsu University of Science and Technology, and Daniel is my colleague as well. We are from the same university. I can roughly introduce Daniel. Daniel comes from Italy, where he did his undergraduate and master studies. After that, he moved to Stockholm University in Sweden for his PhD, and then to Dalhousie University in Canada for his first postdoc, while his second postdoc was at Yangzhou University. He joined Jiangsu University of Science and Technology in fall 2020, where he has been teaching the college physics courses to the international students. So today, Daniel will talk about gravitational entropy. So Daniel, here is your time.
Hello, everybody, and thank you for attending my seminar today. So the title of my talk is some words about gravitational entropy and Penrose Weyl curvature conjecture. So the key word in the title is actually the adjective gravitational, and I will try to explain its meaning as a qualification of the word entropy. Another keyword that I will introduce in what follow is actually density. So what we will look for is the density of gravitational entropy, trying to account for some previous literature studies. So as we know, there are many different approaches to the formulation of a notion of entropy. For example, in thermodynamics, according to Clausius, entropy is the manifestation of existence of an arrow of time. So according to Clausius, entropy is defined as a quantity whose value cannot decrease over the time. On the other hand, Maxwell, Boltzmann, and Gibbs formulated a notion of entropy as well in statistical mechanics. They stated that entropy can be regarded as a measure of disgregation and as a quantification of a number of possible different microscopic realizations of the same macroscopic system. So let's look at the two boxes filled of gas at the bottom of my slide. On the left, we have all the gas molecules scattered in some random positions. That is something that we would describe by using the word disorder. And in statistical mechanics, that will correspond to a state of high entropy. Instead, in the right picture, all the molecules are well packaged on the top left corner of the box. In that case, we will adopt the word order, and that will correspond to a state of low entropy. Why is a notion of entropy from statistical mechanics useful also in black hole physics and in cosmology? Well, in black hole physics, because an observer located outside the horizon can only measure some astrophysically relevant parameters for the black hole, like its mass, its electric charge, and its angular momentum. But an observer located outside the horizon cannot measure the degrees of freedom hidden by the horizon. So the question is how many different microscopic realizations of the degrees of freedom hidden by the horizon can be consistent with the same measurements of macroscopic astrophysical parameters. Likewise, we have the same in cosmology, because we might have a different microscopic realization of our universe, whereby microscopic, I mean we can arrange in different positions galaxies, cluster of galaxies, filaments, and voids, but nevertheless obtain the same astrophysical values for macroscopic quantities like Hubble rate and matter abundance. So in cosmology, the question is how many different distributions of galaxies we can have generating the same observed value of an Hubble function. Newman and Shannon argued that entropy is useful also in information theory, once again, from a probabilistic perspective. Actually, to show that in all this context, we can always use the word entropy, so which means that the physical phenomenon is the same. To show the equivalence was actually not an easy task, it required a lot of work. So now the question is, can we assign a notion of entropy to the gravitational field? And according to the pioneering works of Hawking and Bekenstein? The answer is yes. In the 70s, Hawking published two papers in Communications in Mathematical Physics. In one paper, he showed that the area of the event horizon of a black hole cannot decrease over the time. He adopted some notions of energy condition and the notion of null infinity. And then in another paper, he interpreted such a result as stating that the area of event horizon of a black hole can be a good candidate for the entropy of a black hole. Therefore, this is what I qualified as the thermodynamical approach to a notion of entropy, because in this case, the entropy was considered as a quantity whose value cannot decrease in time. In the same years, Bekenstein also computed the entropy of a black hole, and remarkably, he obtained once again that the entropy of a black hole is given by the area of a horizon surface. I'm using the word remarkably because Bekenstein based his research on completely different physical arguments. According to Bekenstein, entropy of a black hole is a Shannon information entropy. So according to Bekenstein, the entropy of a black hole is a measure of the ignorance of an observer located outside the horizon about the internal degrees of freedom hidden by the horizon. An external observer can only measure, for example, the mass of a black hole, but I cannot have information on what there is hidden by the horizon. So the black hole with the same mass could have formed by a collapse of a star with some nuclear equation of state, or a collapse of some cosmological inhomogeneities. But this information are washed away. And actually, by analyzing the gravitational waves dataset in the merging and inspiraling of two Kerr black holes, it was possible very recently to promote from a mathematical to an astrophysical perspective, Hawking never decrease area theorem. In a subsequent paper, Bekenstein was even more precise about his interpretation of black hole entropy. According to me, he described very, very precisely that the entropy of a black hole given by the area law is the entropy of a pure gravitational field generated by the black hole. And it should not be confused with the entropy of a matter field possibly existing outside the horizon. So let's consider, for example, Schwarzschild black hole. The Schwarzschild metric is an empty space solution of Einstein equations of general relativity. So there is no matter at all. There is not even a Dirac delta for the location of a black hole. But nevertheless, there is a mass. This mass characterizes the horizon. And then according to Bekenstein recipe, we assign an entropy to such an horizon. Therefore, according reformulating Bekenstein interpretation, I will say that the entropy of the area law is the entropy of the mass, but not an entropy of a matter. Indeed, also John Wheeler said that in general relativity, we can have a mass without having any matter. And indeed, we want to assign an entropy to the mass, so to the gravitational field. And this is a striking difference with respect to Newtonian gravity. However, as we know from college physics textbook, entropy is an extensive thermodynamical variable. So it means that it should scale with the size of a system. So our intuition would have expected entropy to scale with the volume of a black hole, not with the area of its horizon. Therefore, this result has been attracting a lot of further work for trying to explain and justify it. There is also another way of reinterpreting the Hawking never decrease area theorems in the language of Ruffini irreducible mass. Once again, in the 70s, in the same years, Ruffini proposed the notions of reversible and irreversible transformations of black holes. Here, the words reversible and irreversible take the meanings, the usual meanings, as in the thermodynamical context. So reversible is a transformation such that we can bring back both the system and its environment back to its initial state. For an irreversible transformation, we cannot do so. Usually, reversible transformation involve only classical physics, while instead, the reversible transformation may require some interplay also with quantum mechanics. For example, in the phenomenon of Hawking evaporation, the area of the event horizon will decrease in time. That will be an example of irreversible transformation, but it requires some interplay, so with quantum mechanics. So in such a context, Christodoulou and Ruffini studied the formation of pairs of particles and antiparticles in proximity of horizon through the Penrose process of a vacuum polarization. Then the antiparticle may follow a geodesic, cross the horizon, and get absorbed by black hole and extract some energy from the black hole. There is, however, a limit to the amount of energy one can extract. So we cannot extract more energy, rather than we should settle down to a value of a mass, which is named irreducible mass. And its square is given by the area of the event horizon. So this is another demonstration of the never decrease area theorem. I will say more from a physical perspective, but the result is the same. And once again, the key quantity is the area, not the volume. Therefore, we should try to understand better why, if this is a judicial result or not. There is a more modern formulation to the area law, which is called the holographic principle, formulated by Tuft in Susskind. According to the holographic principle, a black hole is fully described by the area of its horizon. Therefore, what matters in the description of a black hole is its boundary. So far, I just talked about black holes. However, as we know, general relativity can be adopted also in cosmology for describing the overall evolution of our universe. And in a cosmological context, Roger Penrose formulated the Weyl curvature hypothesis, according to which the Weyl tensor should be a good measure of gravitational entropy. A technical remark now. In general relativity, the full curvature is provided by the Riemann tensor, which can be irreducibly decomposed into a trace part, named the Ricci tensor, and a trace-free part, named the Weyl tensor. The physics, which means the gravitational theory, as the Einstein equations, fix only the Ricci part of a curvature, while leaving free the Weyl curvature. For example, the Schwarzschild black hole, the Kerr black hole, and also Minkowski spacetime are all empty space solutions to the Einstein equations. They have the same Ricci tensor, identically equal to 0, because the stress energy tensor will be 0. However, the Schwarzschild black hole is physically different than the Kerr black hole, and physically different than the Minkowski spacetime. And the difference is put inside the Weyl curvature. Here, the statement that the Weyl curvature should be a good measure of gravitational entropy is consistent with what I was claiming and reviewing before. For example, if we have a faith in some relationship between curvature and entropy, once we study the Schwarzschild solution, the only non-zero curvature is the Weyl curvature. And therefore, that will be the only possibility of finding a bridge between entropy and curvature. Then, according to the Weyl curvature hypothesis, the Big Bang singularity should come with a zero Weyl curvature, whereas the big crunches and black hole singularities due to gravitational collapse should have a large Weyl curvature. Indeed, during the collapse of a star and in the formation phase of a black hole, the entropy of the system increased by a tremendously huge factor. And since while curvature quantifies a tidal deformation, what I'm saying here is that we expect black hole and big crunch singularities to exhibit a very messy and chaotic curvature behavior, because from statistical mechanics, high entropy means high disorder. So something like the Belinsky-Kalatnikov-Lipitz description of curvature. One more remark on why we would expect the Big Bang singularity to come with low entropy. This can be because after the Big Bang, at some later cosmic epoch, the universe goes through the structure formation phase. And in the structure formation phase, local gravitational collapse occurs in some spatial regions rather than in others. And so we have the formation of galaxies, cluster filaments, voids, and many other type of bound objects. However, this will bring to an uneven distribution of matter, an uneven local gravitational field, and to some density gradient. Therefore, during the structure formation phase, we will expect some notion of entropy, not to be confused with the entropy of a matter field, but some notion of entropy associated to the gravitational field to increase because the disorder of the universe is increasing. So you see that we have many different approaches and interpretation to the notion of gravitational entropy. So to the entropy of a pure gravitational field. As I commented, they are consistent with each other. However, finding a practical equation enforcing and taking into account all such requirements has not been a so easy task in literature. For example, here I am reporting about the Clifton-Ellis-Tabakoy proposal of computing the density of gravitational entropy. I will spend possibly some words, time permitting, about it towards the end of my talk. So such a proposal has been adopted by several authors, including ourselves, for describing the formation of astrophysical structures in daytime cosmology. However, you see that this notion of entropy is directly sensitive also to the energy density rho and pressure P of the matter field. So it is a quantity which does not depend only on pure gravitational quantities. So the quantities qualifying the matter field and the quantities qualifying the gravitational field get mixed up in this proposal. Some other authors investigated the square of a Weyl curvature as an appropriate density of gravitational entropy, which means that the square of a Weyl curvature integrated over the volume should reproduce the area of the horizon. We showed explicitly that this formalism provides correctly Hawking Bekenstein area law for 4-dimensional and 5-dimensional Schwarzschild and Schwarzschild anti-de Sitter black holes. But they themselves commented that such a proposal does not meet a general applicability in black hole physics because it fell in the case of a raster Nostrum space-time. Therefore, I think that this proposal is at odds with the Bekenstein interpretation of the area law, because if you remember, when Bekenstein discussed the generalized second law, he was careful in distinguishing between the entropy of a black hole, the entropy of a gravitational field given by the area, and the entropy of a matter field existing outside. Therefore, I think that a good formalism should not be sensitive on the presence of lack of an external electric field, external to the horizon, with its energy density and pressure. Some other authors in cosmology, they proposed to study anisotropic singularities, once again using a notion of entropy, by rescaling the square of a Weyl curvature with respect to the square of a Ricci curvature. However, once again, we can re-express the Ricci curvature as some functions of energy density and pressure of a matter field by using Einstein equations. So also this latter formalism is somehow mixing up properties of a gravitational field and properties of a matter field. So after this literature excursus, I am ready to write black on white the question that we wanted to answer. So we wanted to look for some function chi that we demand to be function of the Weyl curvature and only of the Weyl curvature, such that integrated over the volume of the black hole should give the horizon area. We want our formalism to be the same for all static and spherically symmetric, possibly distorted black holes in 4 and 5 dimensions. So here, the function h of r is a function which involve some no higher parameters, and such parameterization of a metric tensor played some role in testing the no higher theorem with respect to gravitational wave dataset, with respect to X-ray dataset. For keeping our discussion basics to the relevant physics, let's think for now that h, this function h, is equal to 0. You can see I'm not making any assumption on the function f of r. So I want my formalism to be good enough for covering the case of a Schwarzschild black hole, of a Schwarzschild anti-de Sitter black hole, and a Racer's nostrum black hole. So I don't want to make any restrictions on asymptotically flatness properties and on the lack or existence of some energy density outside the horizon. And this is because of the formulation of a generalized second law by Bekenstein. Then we would like our function chi to depend on the Weyl curvature and only on it for enforcing the Weyl curvature conjecture by Penrose. We integrate over the volume of a black hole, so inside the horizon, for enforcing Bekenstein interpretation that entropy is a quantification of our ignorance of the degrees of freedom hidden by the horizon. So we should sum our ignorance for each degree of freedom hidden by the horizon. To make a sum mathematically means to compute an integral. And we want to obtain the area of horizon, well, because all the literature I reviewed. I would like to make it clear that in this research project, we are not interested in searching for logarithmic corrections beyond the area law. The area law is actually one of our assumptions. Also, we are not interested in finding new ways of computing the entropy of a black hole. So it's not a research project like in the Euclidean path integral method and so on. What we want to find is its density. And what we want to show is that there exists at least one explicit way of enforcing all interpretations of Hawking, Bekenstein, Tufte, Susskind, Penrose, and so on simultaneously and consistent with each other. And according to us, the result is yes. So it is possible to find a formalism with a general applicability if we work with the Newman-Penrose scalars or with the Cartan curvature invariant when we will go to 5-dimensional space-times. So the metric tensor I showed you is Petrov type D. So there is no ambiguity on its on the Weyl curvature. There is one and only one non-zero independent component in the language of Newman-Penrose, and such a quantity is psi2. Then our intuition was not to stop at the 0 level of a curvature, but to go at the first level. So to allow the density of entropy to depend also on the Newman-Penrose derivative of such a Schwarzschild. So in the integral, I'm showing that the density of gravitational entropy we are proposing is the ratio of the Newman-Penrose derivative d of psi2 divided psi2 itself. We integrate over the spatial hypersurface volume element, and I will get back very soon on why we should do so. So why we should also choose a spatial hypersurface volume element rather than Euclidean one, or rather than the Pisoduro-Rovelli proposal for the ball. Also, you see I'm integrating up from 0 up to the location of horizon. So I am assuming the existence of an horizon in our space-time. So here I am stopping the integral at the horizon for enforcing Bekenstein claim that what is outside the horizon should influence the area law. There is one numerical coefficient, 1 over 3 square root of 2, that we need to tune by hand. It will be interesting to search for some physically deep, physically motivated coefficient for matching with the 1 over 4 in the area. So our formalism is fully based on the Weyl curvature. So we feel it is an appropriate result for the density of gravitational entropy. Our formalism is purely geometrical because we have not used the Einstein equations. So we have not made any assumption of this function f of r entering our metric tensor. So our formalism is formally the same, as I said, for Schwarzschild. Schwarzschild the sitter, and Resser's nostrum. So it's not sensitive to asymptotically flatness properties, and neither to the existence of lack of densities outside the horizon. And finally, it can be noticed that our formalism applies also to Bardeen, Hayward, and other regular black holes. Indeed, as we discussed 2 weeks ago, it's the horizon which is defining the black hole, not the existence of a singularity. So the holes are defined as space-time regions in which light rays are trapped, in which light rays cannot escape. And so the fact that what is matter, what is important here, is the horizon surface rather than the singularity. This is our way of taking into account the holographic principle by Tufte and Susskind, according to which what is relevant for the description of a black hole is indeed the boundary, its boundary. So this was still a little bit mathematics, but we can also provide some physical considerations and interpretations.
So Daniel, I have one question.
Yes.
So in the previous slides, so I'm confused. So what is this edge? Is this edge appearing in the metric function?
H inside of a square root. H.
Yes, and also those edge appearing in psi too.
Okay, this is the definition of H. So is the last equation. So this was a parametrization for taking into account and for constraining astrophysically possibly distortion of black holes. So here we have some Airy parameters, epsilon k, and here I'm also providing some references. So this is the black hole metric formulated by Johansen and Psaltis.
And what do you mean by f of h in your next slides?
F of r.
No, in next slides you have some f as a function of h prom, for example.
Some f. No, that is not a function, it's a multiplication.
Okay.
Okay, it can be confusing. So it's the function f, for example, the f of Schwarzschild, 1 minus 2m divided by r, multiplied by the h, where h is this function here. So that is a product, an algebraic product.
Okay, I see. No problem. Thank you.
Good. And also, well, finally, D, which can also be some notation, is the Newman-Penrose frame derivative. That in our case will be being static and spherical symmetric will be a derivative with respect to R, with some, however, with some metric normalization. And this metric normalization indeed clean up the metric factors inside the spatial hypersurface volume. So here, this psi2, this Weyl scalar, let's say, is still quite mathematics. However, there is an old paper by Zegres, the gravitational compass. And with paper, it was explained that Psi2 describe a gravitational monopole. Therefore, we can claim that the mathematics of our result is suggesting us that the black hole entropy is related to tidal effects, which seems reasonable because we have a bound object. Then we can also recall the Bianchi identities. And according to the Bianchi identity, our density of entropy, so the ratio of d psi2 divided by psi2, is the Newman-Penrose spin coefficient rho. So here, let's not get confused once again about the notation. This rho is not an energy density. It's named Newman-Penrose spin coefficient. It is the rate of convergence, rho of divergence, of bundles of light rays. So it takes into account the focusing properties of light rays within the gravitational field. And also Bekenstein already Bekenstein said knew that the variation of the area of the event horizon is governed by this Newman-Penrose spin coefficient. And then our result seems once again appropriate, because what we wanted to describe eventually is the change of entropy, because entropy is a function of state in thermodynamics, so it's not relevant so much the entropy of a given configuration because it cannot be measured. Only what can be measured is the difference in entropy between two different configurations. So this is why Bekenstein was considering actually the variation of the area rather than the area itself. And the variation of area is governed by such rho, which by the Bianchi identities can reduce to our density of gravitational entropy. So I would say that our core intuition was to go to the first order quantity in the Weyl curvature. So not to stop at the Weyl curvature itself, but also to consider its derivative. Here we worked with the Newman-Penrose derivative because when we got back to our integrand is a scalar quantity, so it's well defined are an integrand. So up to now, it might still seem that our result is a matter of guess. So let me now try to provide a constructive procedure for obtaining and reproducing it. So we will work in the context of a relationship between gravitational entropy of the Arial law and other charges as discovered and proposed by Robert Weyl. So here we want to stay in the case of general relativity. So we consider a Lagrangian, which contains the Einstein-Hilbert term given by the Ricci scalar R, and possibly a minimally coupled scalar field if there is to account for some matter content in our space-time. When according to the not charge prescription, the entropy can be computed as a suitable two-dimensional integral over spatial sections on the horizon. So here you see I'm integrating just over the angles. In the case of general relativity, the result is very easy. So we just consider as the argument of the integrand just simply one. It will be more complicated once we will go to modify the theories of gravity. So also in this method, the existence of an horizon is assumed because this two-dimensional integral is carried out over spatial sections of the horizon and over the angles. What we wanted to find was the density of entropy, which means we should get a result for an integral with respect to the volume. And the mathematical trick to use is the divergence theorem by Gauss. So by applying the divergence theorem by Gauss, we can recast this Arial integral into a volume integral. What we should do is, first of all, to identify the outward and inward normal pointing to the horizon, which can be done once again quite easily in the Newman-Penrose language, because we are given by the four vectors L and N, which are null vectors, and cross-normalize with -1. Then, before applying the divergence theorem, we should identify the current. And so we can also find it quite intuitively, and we feel by direct computation that the current will be the sum of such two vectors. So just simply by applying the normalization assumed in the Newman-Penrose formalism. And then when we go to a volume integral, we should take the divergence of our current. But having in mind the Newman-Penrose paper, the divergence of such null vectors for static and spherically symmetric spacetimes, as the ones we have been focusing, is nothing else than the spin coefficient rho. So once again, we get our result for the density of gravitational entropy. And once again, we get essentially the variation of the area. Now, I can also justify why we should use the spatial hypersurface volume element. Because when we apply the Gauss theorem in differential geometry, the appropriate and correct volume element to consider among the many proposals one can have is the spatial hypersurface volume element. Let's see if I am consistent also with the astrophysical claim that entropy should increase during the collapse of stars and the formation of black holes. Here I went back to the 1939 paper by Richard Tolman. In that paper, Tolman published a set of exact solutions to Einstein equations, just using some elementary functions, assuming the spacetime to be static, to be spherically symmetric, and also assuming the spacetime to be supported by some fluid obeying to some relevant hydrodynamical equation of state relating pressure and energy density. Here, we are considering just one specific solution, which allow us to make computations. So this is called the Tolman metric form. So R, capital R, is the radius of our star. And also in this case, we have a well-defined surface. So when we were studying black holes, we have a well-defined surface that we can pick out as the horizon, because the horizon can be crossed in one direction only. In the context of stars, I will think that the relevant surface is the boundary of a star, because it can be operatively defined as a surface in which the pressure is vanishing. So we have an operative and physically well-put definition of such a surface. Then we take Maple, for example, the Maple software. We feed it with such a space-time metric, we work out all the relevant computations. We compute the relevant components of the Weyl curvature. Once again, we are dealing with a Petrov type D space-time. And then we integrate from 0 up to the surface of the star, so up to R, up to the location where the hydrodynamical pressure is vanishing. And in this case, we can obtain a closed result for the integral, and we can show that indeed is something smaller than the area of a relevant surface. And this is something, once again, something like the holographic principle, because we are focusing on what is happening on the surface. And here is our interpretation that the entropy of a star is smaller because it's smaller than the area of its meaningful surface. It will be interesting to work more in general to see under which energy conditions or enforced in the Tolman-Oppenheimer Wolkoff approach our formalism will work, and this is still an open question. So far I have considered static spacetimes. However, as I said, general relativity is rich enough and allowing us also to study the gravitational field of the overall universe. So I'd like just now to spend some words about entropy, gravitational entropy in cosmology, why it is useful. Here I am considering a spherically symmetric dynamical space-time as a model of an homogeneous universe. So we have a sort of generalized scale factor, h a function of t. Okay, so once again about the notation, this h has nothing to do with the previous h. It's simply that the same notation was used. So here h is some function of a time that we could interpret as a sort of generalized scale factor. And some persons a lot of years ago were interested in trying to get analytical solutions in closed forms to Einstein field equations. We just focused on the mathematics because that was already a quite rich and demanding problem, because Einstein equations are constituted by a system of coupled non-linear partial derivative equations, not easy to solve. We could found remarkable solutions for both open and closed topologies that I'm listing here. And then in our paper, we tried to add, to see if we can add some physics, if we can assign some physics to such mathematics. For example, we'll see that the equation of state of a matter content supporting such spacetime is what I reported here. We have, in a modern language, for example, the equation of state parameter depends. So the equation of state parameters in this model depends on the background energy density. And in a modern language, this can be regarded as a chameleon field because its properties are sensitive to use of the background. Also, you can see that when the constant c, which is a mathematical constant of integration, when such a constant is at 0, you will have a pressure equal to energy density. This is called a stiff fluid equation of state. That is the hydrodynamical realizations of a massless scalar field. And Zeldovich argued that some primordial epoch of the universe might be dominated by massless scalar field. On the other hand, at later times, we see that when the energy density gets diluted, the pressure does not vanish because there is still a constant C which might be non-zero. And once again, mathematically is simply a constant, but in the context of physics, we can name it as the bug constant of our equation of state. So a constant making the pressure to be different than 0, also when the energy density is vanished. Then once again, we feed the maple with such a metric tensor. The maple is informing us about the energy density, the Ricci curvature, the Hubble function, the shear tensor, the matter parameter, the acceleration parameter, and so on. And then we start once again adding the physics. A meaningful model should come with a positive energy density. And this is setting some constraint on the value of a mathematical constant. See that once again, the physics language to say that we are getting some upper bound of the bug constant. And let's look at the denominator of the Ricci scalar. We have epsilon plus 2ht. So we have epsilon, which can be -1, 0, or 1, depending on the topology. H is the scale factor. So when such a combination, when the denominator is vanishing, you will have a curvature singularity, so a true physical singularity that we can interpret the Big Bang. So the time at which so happen, at least implicitly, will be the Big Bang time. Now, I would like to comment that we can get some physical constraint and possibly abusing a little bit of language, some model selection and parameter optimization by enforcing thermodynamical requirements to our space-time. So here I am mentioning the cosmological holographic principle as proposed by Bosso, according to which the entropy of a physical cosmology will be bounded above by the horizon area in some units. Of course, this should be an upper bound because once we saturate it, we don't have any more a cosmology, but we have a black hole. And then should also check whether the second law of the thermodynamics for the entropy of a matter field holds or not. So in this case, by applying this requirement, we can rule out our model, we can confirm it, or we can also restrict the ranges of validity of the numerical values of a free mathematical constant stemming from integration of Bayesian equations. So here there is some mathematical details, but the take-home message, that I would like to give you about this second part of my talk is that it is possible to work completely theoretically. So just using a pen and a piece of paper for doing computation. And already by doing so, you can extract relevant physical information from our space-time without the need of resorting to Bayesian data analysis and so on, which can be beyond the expertise and which might not be in the toolbox of a theoretical physicist. So simply by working, by requiring some consistency check, some requirements from basic physics, we can already get some information about our cosmological spacetime. Then, of course, if our model pass with such a first test, then you can further restrict the values of a parameter by doing a more complete astrophysical testing. So let me show how the cosmological holographic principle works. We should identify the location of the horizon, which can be found through a solution of a certain algebraic equation. So what we found is that in our class of spacetimes that I showed you before, an horizon can exist only for closed topology, which means we have a real non-complex solution only for closed topology. We solve our algebraic equation, we get the location of the dynamic apparent horizon, and it must be a real positive number. So whatever is inside the square root should be positive, otherwise the horizon will be ill-defined. And here, so simply imposing such a requirement, we will get some further constraint, interplay between the numerical values of our constant on our free parameters. And interestingly, we could relate the existence of the dynamical apparent horizon to having automatically a negative deceleration parameter, and also about not having any Big Bang singularity. Indeed, in a closed topology, if you go back here, is the third possible solution. Epsilon is 1, is positive. H is a sort of scale factor. It should be positive as well. And so the sum of the two is larger than 0, and the Ricci scalar cannot blow up. Then we compute the area of the dynamical apparent horizon. We compute the entropy of a matter field inside it. Our matter is regular matter, so in this model, so there is nothing exotic. So we can safely assume that the entropy density for the matter field scales with the volume of the system, so with the cube of the radius of the dynamical apparent horizon. We impose the entropy of the matter field to be bounded above by the area of horizon, and we get a constraint, an upper limit on the bug constancy. Also remember, okay, so let's go back to here. So here are the solutions to the Einstein equations. We have three constants mathematically, A, B, C. So just mathematics. However, once we get a restriction on their values, those restriction on their values then can be translated into restrictions on the Hubble rate, on the shear tensor, on the matter abundance. So can be translated into some quantities for which we have a well-defined physical. Then the same, we impose the second law for the entropy of the matter field, and we obtain that the second law, so a thermodynamical requirement is equivalent to a cosmological requirement in our class of model, as a lower limit on the size of the universe, or equivalently on its edge. So the take-home message is that we can use thermodynamical consistency check for evaluating the applicability of some solutions to the Einstein equations as cosmological models. At the beginning of my talk, I said that the formulation of entropy as from statistical mechanics is something related to the notion of order and disorder, and can be used for tracking the possible formation of astrophysical structures in our universe. So in this case, we should introduce another entropy, so not the entropy of a matter field, but the entropy of a gravitational field. So this was actually our first paper along the direction of gravitational entropy, and we relied on the proposal of Clifton, Ellis, and Tawakol, because it passes some appropriate requirements for a good notion of gravitational entropy, because it provides an entropy which is non-negative. It provides an entropy which is zero in and only in conformally flat spacetimes. So for example, the Friedman metric is conformally flat. The Friedman metric is homogeneous and isotropic with vanishing Weyl curvature. And by homogeneity and isotropy, let's say we cannot have a formation of astrophysical structures. There are no gradients. So it is reasonable to demand the entropy to be zero in that case. Also, such a notion of entropy quantify the local anisotropies of a gravitational field via a dependence of the shear tensor. Also, is consistent with the Bekenstein entropy of a black hole, and it is expected to increase during the structure formation phase of a universe. And as I said, it has been adopted by many authors for describing and for trying to modeling mathematically the formation phase of our universe, including ourselves. So here I am reporting actually the time derivative. So the over dot is a time derivative of the density of gravitational entropy. So it depends on E. This E is the electric part of a Weyl curvature. It depends on the shear tensor sigma. It depends on the energy density and pressure of a matter field ρp. However, this can be computed very easily with a maple, so we have our result. Now let's go to the physics by making some figures. Here, for the three model parameters, A, B, and C, we chose some numerical values consistent with the restrictions set by the cosmological holographic principle, by boson the entropy of a matter field, and by the second law for the entropy of a matter field. And then we made some figure. Let's start from the lowest one. I am showing you there the time derivative of the density of gravitational entropy. So it is actually a time derivative. Being always positive, it means that entropy is actually increasing over the time. So that our model can be useful for describing the formation of astrophysical structures. However, you can see from the plot in the middle that the Weyl curvature is not monotonically increasing. And our gravitational entropy is increasing also when the Weyl curvature is not, thanks to the increasing magnitude of space-time shear effects, as shown in the first plot. Also, let me remind you that here a dependence on the shear tensor is put in by hand in the definition of gravitational entropy. However, what I think is that a cleaner, a one-to-one relationship between gravitational entropy and the Weyl curvature should be found for enforcing Roger Penrose's requirement in a more conservative way. Therefore, what I would like to, something that I feel should be done is to find a notion of gravitational entropy, which should be increasing on when and only when the Weyl curvature is, and when and only when spatial shear effects are. Indeed, as I said, gravitational entropy quantifies the formation of astrophysical structures as the disorder in the matter content in the matter field is increasing. Then, as bound astrophysical structures are forming, also tidal effects are generated. So this is why I expect in a physically intuitive way, that the entropy should increase together with the increase of a Weyl curvature. And finally, we should demand, I think, the increase of gravitational entropy together with the increase of spatial anisotropies, because astrophysical structures will form in some region of the universe rather than in others. So looking along some spatial directions, we might see a void, or a filament, or a galaxies, or a cluster, so something different. And such a notion of disorder, quantified by entropy, should also be reflected by anisotropy of space-time, quantified by the shear tensor, and some qualitative applications of our class of cosmological model. Our astrophysicist colleagues have identified some large quasar groups by inspecting some data catalogs. The size, the spatial size of such larger quasar groups challenge the claimed existence of an homogeneity scale in the standard model of cosmology. Furthermore, some of these very, very large quasar groups might have formed quite early in the universe. And if we apply standard perturbation technique over a homogeneous and isotropic Friedman background, there will be not enough cosmic time for generating such a strong gravitational collapse. And we think that instead in homogeneous cosmology can make the trick. And furthermore, I claimed that our model can be supported by massless scalar fields that will be relevant in early time cosmology as in the Gregoris model. So let me conclude, also providing some further food of thoughts, leaving you with the following question about the physical interpretation of black hole entropy beyond general relativity. So our formalism was purely geometrical. I simply assumed the existence of some symmetries for my space-time, as the space-time being static and spherically symmetric. I assumed the existence of horizon also. But I never used the Einstein equations. So I never used any specific gravitational paradigm. So if we take some black hole solutions with the same symmetries, so static and spherically symmetric, but arising in some modified gravitational theories, and for sure we know that such solutions have been identified in nature. If we apply our recipe, we get an area. Now the problem is that that area is not anymore of entropy. In many modified gravitational theories, it is claimed that the entropy of a black hole is not anymore given by the area. Our model, our recipe, however, will deliver the area only. So we should investigate and we should discover a combination of curvature invariants, providing the modified entropy law. However, even without knowing that explicitly, we know that for sure it should be different than ours, than the one we adopt in general relativity. So we provided a physical interpretation to the foundation of black hole entropies according to our mathematics. Since the mathematics will change when we consider modified theories, because the density of gravitational entropy will depend on other curvature quantities, the question is, what are the degrees of freedom that are manifesting themselves in the entropy of black holes in modified theories of gravity? And with this question, I think I have exhausted also the time of my seminar.
So thanks, Daniel, for the talk. So any question from the audience? Good to you.
May I ask questions?
Yes?
Yeah, I have a couple of questions. Oh, so first of all, thank you for a nice talk. So do you have any idea how to apply your formalism to, for example, the dynamical collapsing models, like, for example, the simplest one, the Oppenheimer-Snyder? because you mentioned about the collapsing process. I think it's more
Yes.
natural to consider this kind of model and to see how the entropy, based on your formalism, evolves.
Okay, so we have done the computations for the Lemaitre-Tolman-Bombi.
Mhm.
So spherically symmetric, supported by dust. We still apply here, we still apply this formalism. The difference with respect to the case of static black hole is that the divergence of L, of the L vector, Newman-Penrose L vector, and the divergence of the Newman-Penrose N vector is different. So for static and spherically symmetric black hole, okay, so here the divergence is a linear operation. So you can expand it. The divergence of a sum is the sum of the two divergences. The divergence of L is rho, is the Newman-Penrose spin coefficient rho. The divergence of N is mu, is another Newman-Penrose spin coefficient, still related to focusing properties of light rays. In that case, the density of gravitational entropy, we found the explicit result in terms of spin coefficients. It will be the sum, essentially, of rho plus mu. So of two different Newman-Penrose spin coefficient, which will reduce to be the same, equal to each other, in the limit of the static space-time. So consistently also what our static formalism.
I see. And the second question is, since in the static case, you mentioned that the formalism requires the assumption that you have an event horizon, and
Yes.
then why in the dynamical case, for example, in this case, it seems that you don't have to assume the horizon anymore.
No, well, I still have to assume because I needed to stop the integral at the horizon.
Even in the
So
dynamical
for
case, because I couldn't, for example, in the dynamical metric, I didn't see the horizon.
okay, here it was this dynamical metric.
Yeah.
Here, okay, the project was a little bit different. So the metric is the first one, the first line. So we have epsilon, which is a constant, accounting for the topology. We have a scale factor, h, function of p. Then the horizon, also in this case, the horizon can be found. So look here, the left column, second line in black. So here we have a dynamical apparent horizon.
Oh, okay.
The dynamical apparent horizon, so we should identify the areal radius. So we identify the areal radius. The areal radius is here is r square multiplied by what I have inside the square bracket. So let's say the metric coefficient multiplying the angular part in the metric is the square of areal radius. So we identify the areal radius. We take its gradient. We take the square of a norm. And the horizon is where such norm square is vanishing. So this is the definition of dynamical apparent horizon. So this way of so we can find it. This way I can refer to a review. I think it is a Living Reviews in Relativity by Ashtekar and Krishnan about dynamical about horizons in dynamical space-times and their applications.
I see.
So this is one possible way of defining the operatively the horizon in this dynamical tensor.
Thank you.
So any question? So Daniel, maybe I ask you a similar question. Okay, why does the entropy density doesn't work for the iron black hole?
I'm sorry?
I mean, why does the entropy density doesn't work for the iron black hole? I mean, in your slide you mentioned about this.
Here this proposal.
Yeah.
The square of Weyl curvature, it doesn't work because if you apply this, it works, let's say it has a limited applicability. So it works in some cases, but it fails for research nostrum space-time. So for a static, spherically symmetric electric charge black hole, the square of the Weyl curvature integrated over the volume does not give you the area of horizon. But a good formalism should come with a general applicability. We think that the formalism should be the same for all possible vectors. So here this is a direct computation. One can do a direct computation. So for example, with Maple, you compute the Weyl curvature with Maple. You take the square and you'll see directly that its integral does not give you the area for research nostrum.
Okay, I see. Another question is,
Yes.
what do you mean by the entropy of a matter? I mean, outside the event of a horizon.
The matter of an entropy. Okay, so here
Yeah.
will mean. So here this is the paper about the generalized second law of thermodynamics by Bekenstein. By entropy of matter, I will mean the entropy you are familiar with from college physics textbook. I will mean the entropy of a matter field is the entropy that we also have studied when we study the gas expansion in college physics. So it's the usual entropy, let's say with no tricks. Instead, the entropy, so is the entropy as we learned it from college physics. Instead, the entropy over a law is the entropy of the degrees of freedom hidden by the horizon. So it's something different. So the entropy over a law is the entropy of our ignorance of what hidden by the horizon. So the entropy of a matter field outside the horizon, I would say, is simply the usual entropy for any matter field that we study in college physics.
Okay, I see. So, any question from the audience? So, tell you maybe we can stop recording, I think.
Well, perfect. Okay, so